Okay, you guys. So in this part of the lecture, I'm going to start introducing ring opening metathesis, ROM. And when I first introduced this, I told you that it's just the complete opposite of ring closing metathesis. And so one of our first examples in ring closing metathesis was the following dyne system. And I'll go ahead and number it just like I did before. And I told you you treat it with Grubb's first generation catalyst. And your product was a five-membered ring. And I'll continue to number this as well. And not only is it a five-membered ring, but you have a pi system, a double bond that's formed within the ring, and you have a byproduct. And the byproduct is made up of the two carbons at the end of the skeletal chain. Let me draw out the hydrogens on here. Okay. And so, again, it shouldn't come as a surprise that for ring opening metathesis, everything that was product is now starting material. And everything that was starting material is now product. Okay. The catalyst, because it gets generated and it is a catalyst, it continues to be a reagent. And so luckily for us, the mechanism follows the same procedure that ring closing metathesis does. So let me go ahead and jump into the mechanism of ring opening metathesis for this structure. Okay. As before, you start off with your catalyst. And you introduce your starting material. I'll go ahead and start off with my five-membered ring because that's what I'm trying to open. And just like before, our first step is ligand association. Nothing has changed from before. Same step. The double bond is associated to the ruthenium. Just like before, our second step is ligand dissociation. Our phosphine group pops off. Give myself a little bit more space here. Exactly first, same two steps. Next step, just like with ring closing metathesis, we've got our pseudo-migratory insertion, where we form our four-membered ring. Four-membered ring. Let me go ahead and draw the four-membered ring. Now, usually these are tricky just because you're forming a ring next to a ring. So it can be tricky to see sometimes. There's our metallocycle. Just like before, it collapses, and it collapses to open up the five-membered ring. Okay. Again, you're trying to open up a ring. So when it collapses, you're trying to form the five-membered ring. If you don't open up the five-membered ring, then you're just going back to your starting material, right? And so you've got to open up that five-membered ring. So let me go ahead and draw out what that product looks like. Please notice that our ruthenium is now part of our skeletal chain. And also notice that we've got an alkene on the other end. It's not the alkene that we want, right? So we have to come back later on and take care of this. But at the very least, we've got our ruthenium as part of our chain. Now that we've got ruthenium as part of our chain, we introduce our alkene, which is our ethylene. And just like before, there is ligand association. Just like before, we have a pseudo-migratory insertion. So let me write down ligand association here first before we move on, followed by pseudo-migratory insertion. I want to give myself enough room. Please notice that it's all happening between those atoms, right? So I have to form my four-membered ring right there. So even if it looks a little weird, that's where my four-membered ring is being formed. It collapses, and I've completed the left side of my structure. So you can see that the left side of my structure is done. I just need to worry about the right side of my structure. I need to get rid of this phenyl group. And the only way to really get rid of it is to regenerate my catalyst. Because if you noticed, when this collapsed, it also formed a double bond between a ruthenium and the end carbon, CH2. So I want to exchange that CH2 with my phenyl, right? And so we're going to jump in and do a ligand association again. If I don't have enough space, I'll move everything to the bottom. And notice that I keep drawing the CH3s. So there's my ligand association product. Now it does a migratory insertion, a pseudo-migratory insertion. Let me go ahead and draw out the arrows. And just like before, notice that it's occurring between those four atoms. So it's going to look a bit funky. And just like before, it collapses and it generates not only my product, but the precursor to my product. So there's my product. And let me go ahead and draw out the precursor to my product right underneath. You can see the double bond. All I need, like before, is to add my phosphine ligand. So let me remind you what the precursor to my product, to my catalyst is, followed by the addition of my phosphine ligand. So pretty clever. Okay. Notice that all the steps are the same. You form ligand association is your first step. Ligand association is your second step. You form two metallocycles along the way, and you regenerate your catalyst at the very end. Exact same mechanism. Okay. Now, in this case, we used ethylene as our second pi system. It doesn't always have to be ethylene. It can be different pi systems. And so what I'd like to do is give you a different example. Again, it doesn't have to be just ethylene. Ethylene is just the simplest unsubstituted alkene, right? You can have other systems as well. So let me give you example number 2. Not surprisingly, if your alkene is different and it's substituted, then one of your ends in the open chain system is going to be different, right? Because it's substituted now. So what do I mean by that? Let me go ahead and give you the product to this. And then we'll go ahead and do the mechanism. Okay. So we've got the following structure. And it's clearly a bicyclic system. Okay, a 4-membered ring right below the 5-membered ring, or fused to a 5-membered ring. And then, of course, we've got our alkene, a different molecule. And what I'll do is I'll star this carbon and call this 8, 9, 10, 11. If you want to number the starred carbon, by all means, you should number it just to keep track of it. But because I've done this reaction before, I just want to try to highlight the end carbon to show you what's happening. Okay? Completely up to you. And I'll continue to draw the or write in the numbers and star that carbon so that you can keep track of everything. Let me give you what the product of this molecule looks like. Okay, so notice first of all that it's the four-membered ring that has the alkene, right? So it's the four-membered ring that we are going to open up. Okay, the five-membered ring doesn't open up because there's no pi system between any of those carbons. So it's the four-membered ring. So that's why the five-membered ring remains intact. Let me go ahead and number the carbon so that you can keep track of everything. Okay, so you notice that I have got carbons 1, 2, 6, and 7, which made up the four-membered ring. It was opened up, and now carbon 1 is bonded to the starred carbon, and carbon 7 is bonded to carbon 8. Okay, so let's jump into the mechanism. Just like before, we always start off with the ruthenium catalyst. Mhm. Just like before, you can start off with the ring or you can start off with the alkene. What I'll do is I'll go ahead and do both. Okay. Let me start off with let me start off with the ring. This is ligand association. Very similar to what we had before. Excuse me. Our step number 2 is ligand dissociation. So we lose a PCY3, a phosphorus group. Just like before, we do a pseudo-migratory insertion. Again, because we're coming from a four-membered ring and we're forming a four-membered ring, it's going to look a little intimidating and overwhelming, right? We're forming a four-membered ring metallocycle. Pseudo-migratory insertion. Pretty clever. A little scary and a little overwhelming, right? If you need me to continue to number my carbons, let me continue to number my carbons. Just like before, it collapses, and it collapses in a way that you open the four-membered ring that was originally formed, right? And so let me go ahead and show you how that happens. It's collapsed, it's opened up my ring, and the ruthenium is now part of my skeletal chain as well. So let me draw that out. Notice that the five-membered ring remains intact, which is exactly what we want. So carbon 1 is now double bonded to my ruthenium. Carbon 6, draw my bond to carbon 7. And carbon 7 is now double bonded to my carbon holding my benzene. Okay. Now I can go ahead and now I can introduce my alkene. And I'll go ahead and number that too. 10, 11. And we have ligand association. I'll number my carbons in a second. Just want to draw out my structure, or redraw it because it's the same thing as above or to the right. I've got my a double bond bonded or associated to my ligand. I do my pseudo migratory insertion. And I form my four-membered ring. I might not have a lot of room, so I'll try to maneuver a little bit around. Okay. It collapses. And so now you can start seeing how it's looking like my product. At least the left side of it is looking like my product. Let me draw that first. Oh, sorry. Let me try to see if I can. Oh, it's getting really small. Notice how the right side is done. Carbon 1 is bonded to that star carbon. Now I have to worry about the left end. Very similar to what we had done in our previous examples, right? When this metallocycle collapsed, it formed the following ruthenium system. It formed a carbene with carbon 8, which I obviously don't want. I want to regenerate my catalyst and it's perfect. So I've got to exchange my carbon chains, right? So again, I introduce the ruthenium that I just made for ligand association. Let me go ahead and draw that out. Let me go ahead and continue to number it so that we can follow along and I know where things are being added. It does a pseudo-migratory insertion. And it forms its four-membered ring. Please notice that when I arrange the ligand association, I try to arrange it so I can see the carbons bonding together. So in this case, I knew carbon 7 and carbon 8 had to be bonded together. So I fixed the ruthenium system so that carbon 8 was facing the top of the ruthenium, right? So it's well positioned to start forming the metallocycle. And that can be a little difficult to get used to. I'll continue to number. I just want to go ahead and draw out my metallocycle. Oh, sorry. And you can see that carbon 7 and carbon 8 are now bonded together. Now it can collapse, and it can collapse to form a double bond between carbon 7 and 8. And it forms the precursor to our catalyst. So it's provided us with our product. And I go ahead and draw out our product up here. Let me go ahead and number it. So there's our final product. Here's our precursor to our catalyst where we just have to add our phosphine ligand for ligand association. Okay? Really clever. Please notice that because this is a symmetrical molecule, right? This molecule is symmetrical. The long chain could have been added to the other side. Perfectly fine. And the star carbon could have been added to the right side. They're the same product either way. I just specifically did it this way because I wanted to stay continuous with the numbers. That's it. That's all I wanted to do. But if you add carbon 8, 9, 10, 11 to the left side and the star carbon to the right side to open up the four-membered ring, absolutely perfectly fine. Okay? So this is the mechanism when you're starting with your four-membered ring. What if you want to start off with your alkene, i.e., your aliphatic chain? So let's do that mechanism. So I'll call this mechanism number one, mechanism number two. Start with my aliphatic chain. We have our ruthenium catalyst. I'll continue to also number my carbons, just like I did before. The mechanism doesn't change. First step is ligand association. The rules don't change in the sense that you always want to add the ruthenium to the internal carbon, i.e., the more substituted carbon. I'm running out of room. Step two is ligand dissociation. So I lose a phosphine ligand. As I forgot to number. Want to make sure we follow along. Just like before, we do a pseudo-migratory insertion. Let me draw my arrows to this. Again, notice how the ruthenium, oh, I don't like that arrow, is adding to my more substituted carbon, carbon 8. That's rule number one, right? Form my metallocycle. It collapses, and now the ruthenium is part of my chain. And just like before, I form styrene. Let me star my carbon so that you can see where that last carbon end is. And now I form my carbene with carbon 8. And now I go ahead and I introduce my four-membered ring cyclobutene, excuse me, for my ligand association. I'll go ahead and number this. So my four-membered ring is now associating with my metal. Okay. Now it does a pseudo-migratory insertion. Again, I've set it up so that carbon 7 and carbon 8 are bonded together. But again, carbon 8 can be added to carbon 1, right? It's a symmetrical system. So perfectly fine either way you go. Just like before, I form my four-membered ring. It can feel a little overwhelming. It's a pretty tall structure. The five-membered ring stays as is. And I'll continue to number. Just give me a second. Again, the metallic cycle collapses, and it collapses to specifically open your four-membered ring, right? Because that's the whole point of ring opening metathesis. You have to open that ring. And this is perfect. I've added one side of my chain, and in this specific mechanism, we were able to complete the right side of the product first. I might be running out of space. So I might have to move the mechanism further down. Let me number. Again, please notice that the right side is done. Now I just need to go ahead and finish up the left side, which is perfect because I've got to introduce my styrene that I made initially, right? So let me go ahead and take what I made here, and I'll go ahead and finish the mechanism at the very bottom, okay? I didn't give myself enough space. Let me continue to number it. I introduce the styrene. Remember the styrene, the carbon end is the starred carbon. It's my ligand association step. There's my alkene associating to my ruthenium. I do a pseudo-migratory insertion. And so you can start seeing the introduction of the star carbon bonded to carbon 1. It collapses to not only form the desired product, but precursor to my catalyst. Let me draw out the precursor to my catalyst first. And my final product. And then finally, of course, ligand association of the phosphine ligand to regenerate my catalyst. Don't forget to always regenerate your catalyst. Okay. The point being, I'm just showing you both mechanisms, is that you can start with any one of the alkenes or olefins. Okay. They should give you the exact same product, which is really nice. So regardless of what you start with, it's perfectly fine with whichever one you start. You should get the exact same product. Okay. Now, I'll go ahead and stop here, but in next week's lecture, I'll continue to do ring opening metathesis, but the mechanisms are going to be, I think, a little bit more interesting because you will be doing ring opening and ring closing metathesis all at the same time. And so you're going to be opening rings and forming rings all together, which is really clever. And then we'll finish off with cross metathesis. Okay? Okay, I'll go ahead and stop here for this lecture.